Okay, so we've established that our f sub I are force corresponding to the sample point of our ith subinterval of our T partition is this, okay? And that's, of course, I've rewritten it here, f sub I, and I wrote it as f sub I star. Probably wouldn't actually write it that way, but I wanted to indicate that this is the f sub I you get if you use the sample point in the ith interval of your T partition. Okay, it's going to be this. And the only difference between the expression I've got here and the expression I had here is that in the first place, this square root is squared. And in the second place, I'm going to have a T sub I star squared here and here that I can factor out. Okay? So when I square this thing, I just basically lose the square root sign. So all I've done here really is I factored out the T sub I star and I've removed the square and the square root sign. And I get this expression, okay? And then that's multiplied by your R of Ti star, which is this, that I haven't written out, divided by the magnitude of this quantity. And I haven't written that out, but it's going to just be the square root of what I've got here. Which gives us then, in the denominator, the square root of what I had here times what I had here is the 3/2 power of what I had here. So I'm just going to write 3 dots there because it's, you know, a fairly long expression. We don't want to use a lot of space. We're not actually going to do this integral. You're welcome to attempt if you wish. But it's just this, g little m1, m little m2, times the 3/2 power of this mess, multiplied by your R of T sub I star. Your delta S sub I vector is, well, it's in this case, we don't have to use derivatives to get the delta S sub I as we usually do. Although we could, and we would end up with the same expression, but it's just your x2 minus x1 times delta Ti times I, plus y2 minus y1 times delta Ti times j. You take this, you dot it with the R of Ti star expression, and you get this, okay? Which is this thing here, multiplied by this dot product, and you continue, okay? However, your function is a gradient of f, so we can integrate it just by, again, taking the difference of the potential function f between the 2 points. And I think, actually I'm not even sure we did that. Yeah, we did that. Losing track of what we've done. I believe we did that somewhat previously, where we got the big G little m1 little m2 times 1 over r2 minus 1 over r1. So when we integrate this, we get an integral which is going to end up being equal to this. But this isn't a really good path to integrate over. Although this will work out. You can go through the details of this. We didn't have time to do it, and I'm not going to take time here. Okay, we're going to stop, and we're going to look now at the way the integral would look like if you spiraled out. Okay?